Thank you very much. It's a great pleasure being here at the Institute. I'm recovering from a lengthy period of fairly heavy administrative duties. So this is a very, very nice place to be in indeed. What I'm talking about today is not the latest result, but it's a result which fits in quite well with the program of this theme. So I thought I would report on it, and there are also some new aspects which have come up recently. So first of all, let me say that this is joint work with my collaborators, Sam Grushevsky and Orsola Tommasi. And it is about the cohomology, or rather the stable cohomology of AG and its compactifications. So let me just set the scene. For me, AG is the moduli space of principally polarized abelian varieties. Everything I'm going to do will be over the complex numbers, so I'll always think of that space as a quotient of Siegel space by the integral symplectic group, and unlike yesterday I'll write sp2g of z, but that's a matter of notation. I'm sure you are familiar with Borel's theorem, which says the following. Goes back a long time. It's 1974. It says that the cohomology of these spaces stabilizes in the sense that hk does not depend on g in a certain range. So let me put it like this. Cohomology of AG stabilizes, i.e. HK of AG, and everything I'm going to do will be with rational coefficients, is independent of G for k less than G. More precisely, we can write this down. The stable cohomology is 3D generated, so we can say that HK of AG rational coefficients is the degree k part of the polynomial ring x2, x6, x10, etc., where x2i has degree 2i. Okay, so that's the situation. Let me make some remarks about this. Of course, the way to think about it is that this is a theorem on group cohomology. Cohomology for the symplectic group. Sorry? I'll say something about the generators in a moment. So the generators, so the x2i here, these are well, they're also often referred to as lambda I, and that is the I-germ class of the Hodge bundle. Is that your question? So, in other words, the cohomology is generated by lambda 1, lambda 3, lambda 5, etc. And you ask, why is the lambda 2 and the lambda 4 not involved? The answer is because there is a relation which says something like this. So you can express the even lambda by the odd lambda. So this is why only the odd germ classes appear here. Okay? So that's, and now, and that is crucial for everything to work, is that this generalizes to local systems. So if we have, say, rho in representation, P2G, then we can associate to it a local system again, they came up yesterday in Dick's talk, and the irreducible representations, they correspond to representations V lambda, and they are enumerated by Young diagrams. And the same phenomenon which happens for the cohomology of AG also happens for the cohomology of these local systems. So this is a result due to, well, decline, which says the following: the cohomology of local system stabilizes, and it's in the same range, and it's very easy, in fact. Well, the result is easy. What one can show is that the HK of these local systems it's either what I wrote down over there, if we have the trivial system, in other words, if we are in the situation of Borel's theorem, or it just vanishes in the range K less than G. Okay. So that's all known. And the question I want to discuss here is there stable cohomology? Sorry? Well, I found it, I mean, I found it in your paper, so I didn't. Yeah. Yeah.
But then I needed a better stable result. I asked him what the better result was.
Okay.
Because you get better stability if the split form of the group.
Yes. Yeah. Okay, so it's a. Okay. Anyway, I certainly got it from your papers. So what I want to discuss is is there a stable cohomology of compactifications of AG? And I'll discuss which ones in a sec. And one remark is that this is not immediate, that one should expect something like this. For example, if you take the case of MG, so MG has stable cohomology. This is, of course, Hara, respectively Matz and Weiss, who identified the generators. But MG bar does not. For the simple reason that if G grows, the number of boundary components grow, and then the B2 will grow. So it's not something which you can always immediately expect. Now, of course, the easiest, well, not the easiest, but the smallest in some sense compactification is Satake, which is a set. It's just AG, and then you add all the AK for K less than G. And there it's a well-known and classical result, theorem, which is Charney and Lee. We're talking about 1983, 84. Which says that HK of AG Satake stabilizes for K less than G, and one can also say what the dimensions are. The stable cohomology is freely generated by classes lambda 1, lambda 3, etc., and alpha 3, alpha 5, alpha 7, where the alpha I, the alpha j is in H2I, Q. So the lambda I you should think of as extending the lambda I which we saw in Borel's result. The Hodge bundle doesn't extend, but the classes extend to Satake. I mean, the Hodge bundle extends to toroidal compactifications, not necessarily, not to Satake, but the classes extend. And then there are some new classes. And these new classes are fairly mysterious. And there is one thing I've learned very, very recently from Eduard Leuinger. And it was always assumed that the alpha j would not be algebraic, but I don't think there is any proof in the literature, any concrete proof of the fact. And in fact, I've learned just a few days ago from Eduard Leuinger that the alpha j are not, I mean, he communicated to me a proof that these are not algebraic classes. So, okay, this is what happens here. Now, the other question is AG tor. So if I take toroidal compactifications, can one then expect or hope? It's very singular. Well, you can say it in homology, and it's not from algebra. Yeah, yeah. I mean, I mean, you can phrase this also as, I mean, the dimension of homology groups will be independent, yeah. And then these are not by algebraic classes.
Are there projections into the gradient of the weight filtration algebraic?
I don't know. I have to think about that. Well, I mean, I think what Eduard proved is that they are of Hodge type 0, 0. Does that help?
Yeah, but so they would project into some 0,
Yeah.
0, 0 instead of,
Yeah.
but this guy would be some sort of,
Well, I mean, the way that this is described is sort of very abstract. You take the space, you associate some CV complex to it, and then you look at the cohomology of that CV complex, CW complex. Okay, maybe we can discuss that. Is this still okay? Hmm? Yeah? Is that okay? Can you? Sorry about this. Right.
Sorry to put it yourself. All right.
Okay, thank you. So, of course, as you know, there are several toroidal compactifications, and I don't want to go into all the details of that. There are two I want to discuss. There is what's called the second Voronoi. And the second Voronoi is nice in the sense that it is a modular compactification. So there the boundary points have some interpretation in terms of the generate abelian varieties, and this was shown by Alexeyev, Olson, etc. But there is also the perfect cone, or first Voronoi. And that is also interesting because it has the nice property that this is a canonical model in the sense of the minimal model program, at least if G is greater than or equal to 12, and that was as a result of Shepard-Barrett. So both of these occur, and they both have geometric nice meanings. So they are worth looking at. And the first remark is that one cannot expect stable cohomology for AG more. And the reason is very much the same reason as that for mg bar. The reason is the following. If we look at LG, call this the number of boundary components. And that grows with G. That is a result due to Baranovsky and Grushevsky. And these will give independent classes. In fact, it's fairly dramatic. If you look at the number of components, boundary components, it's 1 for genus 2 and 3. It is 2 for 4. It's already 9 for 5. And for 6, it becomes more than 20,000. Yeah. So combinatorially, this just explodes. Yeah?
That means that this G minus 3 guy is not the optimal.
No. No. But I don't know. I mean, this is the bound which we can immediately write down. Okay. So where do we go next? Yeah, let me state some results, and then I try to explain to you how one can prove this, and then at the end I'll discuss a few more results. So one of the results is, in a way, the main theorem. Is the following, and this is now slightly different from the way I wrote down the results before, and I'll comment on this. The cohomology groups and now I look at those close to the top dimension. The dimension of the space, the real dimension is g times g plus 1. I look at the ones close to this top degree are independent of G in the range K less than G. Okay. So in a way one should think of that as a result on cohomology with compact support. And of course you can sort of rephrase the result for AG by doing compact cohomology with compact support, because the AG is, well, up to finite quotient singularity is smooth. But the perfect concomitation, that is singular. In some way that one can say something about the singularities, for example, they are canonical singularities, but it's a singular space, yeah, and one cannot expect Poincare duality to hold. So we are here really in the top degree. Why this is, we'll see, will become clear, I think, when I say something about the proof. And one can also, of course, ask the same question about Satake near top degree. And then one can also say something there. Hg g plus 1 minus k Hg Satake stabilizes for k less than g. The stable cohomology is freely generated, and dual to the free algebra generated by the lambdas. I mean, this is a relatively easy theorem. This is about the perfect compactification. This is a much harder theorem. but I thought I would just state it just for the sake of completeness. Okay, so that's a first statement of results. As I said, I want to say something about the setup and how to prove things, and then I'll come back to some more general results at the end. So let me next discuss universal families or other and their stable cohomology. So what do I mean by universal families? So I take the universal family. Of course, this has to be right over the stack, or you have to go to level structures over EG itself. There is a comma family, but not a universal family. But well, you can work with level structures and then equivariantly, which is perhaps this here. Yes, 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 yes. Yeah, yeah. Okay, and then we look at the fiber product. And copies of that for AG. And the first statement I want to show is that this has stable cohomology. So there are very natural possible generators for cohomology around. So for this reason, we look at PI, the projection onto, say, one factor, or PKJ if I project two factors, the ith and the jth factor. And then we have classes Ti, which is the pullback of C1 of the theta divisor. I have to specify, to be precise, what I mean by theta divisor, and by theta divisor I always mean that it's trivial along the zero section. You have to normalize it. Yeah? But you have a theta divisor in the universal family, and you can pull those back. With PKJ, these are the pullbacks of C1 of P, where this is the Poincare bundle. Again, we need to trivialize along the zero section. It doesn't really matter, but to make this well defined, we have to do this. And then the first result, what proves is this. Position. HK. All these fiber products of universal families stabilizes for K less than G, and the stable cohomology generated freely by the classes I've just described, classes Ti and Pjk. Okay. Sorry? Oh, yeah, thank you, yeah. Over, thank you, the stable cohomology what's the idea of the proof is, well, we have this vibration, and then the first thing is we look at the Larry spectral sequence. So we look at EPQ2, which is the HQ, AG, RQ, P, n times lower stuff of Q. And this degenerates by a very classical result of the link. That's the first. And the second is use representation theory to count the number of trivial summons in RQ, PN, lower stuff of Q. And the point is, it's only by what I said before about the stabilization of the cohomology of local systems, it's only the trivial summons which need concern us. For the other, all the other summons have in the stable range have no cohomology. So that's what makes it all work here. And the third point is this: compare this to the monomials in the Ti and the Pjk, which fulfill no algebraic relation in degree less than G. And then just by counting, you see you get sufficiently many independent classes. Okay, in some ways, that is sort of the, well, the baby case which makes things work. And this is why I mentioned it. So why is that the crucial case? So this was number 2. Let me, number 3. General setup. I want to avoid as much of the machinery of toroidal compactifications, but I can't do it entirely. So here we have perfect cone. And this sits over Satake. This is true for all toroidal compactifications. And Satake is stratified by AG, AG minus 1, AG minus 2, etc. down to A0. And then I look at what sits over these stratas upstairs. Of course, there's the big open set AG, and this is sort of beta 0, 1, beta 0, 2, beta G. So, and if you only think about this part here, which sits over AG union AG minus 1. This, by the way, is what's called Mumford's partial compactification. But so here we have to go, of course, deeper into all the strata. So the beta I 0 is, if that's phi inverse of AG minus I, and the beta I is phi inverse AG minus I Satake. And now one fact is the following, and this is special to AG perfect cone. The fact is that the codimension of this strata is I. So if we go deeper into Satake, what we add gets smaller. This is absolutely false, for example, for second Voronoi. For second Voronoi, you get down here, and somewhere here, new devices pick up, which lie over these small parts of AG. So this is what really is special about perfect cone, and why this makes it work. Okay. The next thing is the strata beta I 0 are themselves stratified. So something like this. Beta I 0 is the union of a sigma, beta I 0 sigma. And what is the sigma? The sigma runs through GLIZ orbits of cones in perfect cone decomposition of the irrational closure of the space of positive definite symmetric I by I matrices such that sigma contains matrices of rank I. Okay, so these toroidal compactifications, in a way you have to do something over each cusp, sort of over each of these AKs here, and you have combinatorial data, so you take this cone of positive definite matrices, you take what's the rational closure, and you have to have a cone decomposition of that. And that has to have all kinds of nice properties. In particular, also, it has to be invariant under the GLIZ action, and only finitely many orbits. And there are, I mean, this is reduction theory of quadratic forms. There are several ways you can do it: second Voronoi, perfect cone, first Voronoi, central cone, etc. Well, not etc. These are the three classically known ones. And they, in each case, give you the combinatorial data for one of these toroidal compactifications. So this is what you get. And these strata, they have rather nice structure. So taking one of these cones, sigma, we can associate to it a torus bundle over xg minus I copies of this universal family. So get these torus bundles over these fiber products of universal fibers. And then I take G of sigma, which is the stabilizer of the cone sigma in GLIZ, and then the beta I is the quotient of this torus bundle divided by this group. So this makes things approachable. Yeah? I have a fiber product of universal families. Over that I have a torus bundle, C star to something. I can try and study the cohomology of that. Then I have a finite group acting, so I then have to ask what part of the cohomology is invariant, yeah? And that gives me the cohomology of that particular stratum. Okay, maybe one more remark, namely that the codimension of such a stratum is the dimension of the cone sigma. So cone sigma spans some space, and that is the dimension we are talking about. Okay, so let me give you one example. What about the B2? So B1, this is Mumford's boundary. Yeah? What about the next step, B2? That has two strata. One comes from a cone called sigma 1 plus 1, and the other comes from a cone called sigma K3, which has nothing to do with K3 surfaces. That has something to do with graphs, but not with K3 surfaces. So what is this sigma 1 plus 1? That is the two-dimensional cone spanned by the rank 1 forms x1 square and x2 square. And what is the group? This is generated by, well, you can exchange x1, x2. You can send x1, x2 to minus x1, x2. You can take everything that's generated by these two. What is the torus bundle here? The torus bundle. This is a C star bundle over xg minus 2 copies of that. In fact, it is the Poincaré bundle, in this case minus the zero section. So one can actually identify that nicely. And then you're in business. I mean, you have the Poincaré bundle here, minus the zero section. You can ask about the equivariant cohomology, can compute it. Yeah, I could write down now what the generators of the invariant cohomology are. So this stratum here has codimension 2. And the second stratum here is the sigma K3. That is spanned by x1 square, x2 square, x1 minus x2 square. The group here, you can write it down, it's generated by, you can exchange x1 and x2, you can both multiply by minus 1, and And there is one where you take x1, x2, you map it to x1, x2 minus x1. So again, finitely, well, nice group. And now, this has dimension 3. So the codimension here is 3. So here I had a C star bundle. To get down one dimension, the C star, the torus bundle becomes trivial. So in this case, there is no torus fiber. So this is just simply the TG, the XG minus 2 copies. But of course, once you go deeper into the boundary, you get lots and lots of these cones and lots of these strata, and there's no earthly chance that you will enumerate them. So if people do that with big computers, and perfect cone is a bit easier than second Voronoi. So with big computers, you can get up to genus 8, 9, possibly for some questions 10, where you can write down complete lists, yeah, or make some results, have some results. But in general, this is hopeless to enumerate these things. But still, one can do something. Now, let's do the following. Prove the cohomology of the torus bundles stabilizes. But the point is that in a way, the cohomology of the fiber product of the universal family stabilize, and the torus part, yeah, that does not depend on G. Yeah? So the torus part is fixed, and that's why this is feasible. Sorry? The what? The yes, I mean this is this remark I made that the codimension, yeah, if you go deeper into the boundary, the codimension grows. Is that, if that's what you mean? But the cones, okay.
Yeah, so I'm saying, so I'm looking only in small for dimensions, but
Yeah.
then I go higher.
Yes.
So I can see like 1 point, 2 points.
Well, you get finitely many, but that's all you can say. Yeah. I mean, as I said, up to genus 9 or 10, there is possibly a chance.
No, but even what we wrote.
Yeah, I mean, if I'm over a fixed stratum in a G Satake, the I is fixed. The I is fixed. Yeah. Okay. Yeah. That's the point. That's the point, of course. Prove that the G sigma invariant cohomology stabilizes. There's nothing really which depends on G with these groups. And thirdly, use Gaussian exact sequences for cohomology with compact support, and this is where we get sort of into the top degree. And all these strata are, of course, essentially smooth, yeah? To glue the different strata. Okay, so this is what you then, the program one has to do. It works. Okay. So, let me maybe give a few further results. questions. I'll come back. Yeah, you can. I mean, yeah. Between which groups? That's a good question. So you're asking about the stabilizing map, yeah? Because if you take AG and AG plus 1, you have an embedding of 1 into the other. Yeah? So this is actually a tricky part here, in the sense of, yes, there are stabilizing maps here for each of the strata, yeah? And then you go to compact support. You go from small degree to high degree, and these things are still compatible. So in that sense, you get a stabilizing map. But it's not sort of immediately that I can say, here's a map from one space to the another, and that's the pull back or the push forward or something. Yeah? So the stabilizing maps, they come here in this strata. And we can say something about the generators. For small degree, the generators can be written down explicitly. So, further results. Proposition. Betty numbers for small k can be computed explicitly. K, beta k, 2, 4, 6, 8, 10, 12, 1, 2, 4, 9, 18, 38, 83. It grows quite quickly. Something I should have said earlier on, but let me state it here. In the stable range, and I now go to homology, it's 1 minus k can be, or is generated by algebraic classes. Okay. There's another remark I want to make. There is something called a matroidal the matroidal locus. So the matroidal locus is a partial compactification. And I write something down which doesn't really make sense. It's the intersection of second Voronoi and perfect cone. So this is a partial compactification. What do I mean by this? I told you that for toroidal compactification you take AG and then you take strata belonging to certain cones. And there are some cones, the so-called matroidal cones, which are contained both in the perfect cone and in the second Voronoi decomposition. And if you take the partial compactification by adding the strata associated to these cones, you get a big open set, and it's the biggest possible open set, which is contained in both Voronoi and second and perfect cone. And that's quite a useful thing, because this contains closure of the Schatkirch locus. So this is these are results due to Alexeyev, Burniate, Melo-Viviani. So what I'm saying is there is this useful partial compactification, and that is also can also be treated with this method. so this is the next proposition. The cohomology hg times g plus 1 minus k of this partial compactification with compact support, which is isomorphic, because now we again have Poincare duality. This stabilizes in degree k less than g. So this is well, this is smooth up to finite quotient singularities. Yeah. So there we can also apply our method, and Betti numbers can be computed. For small k. Okay. So that's one thing. And the last thing I want to mention in the remaining 2 minutes which I have is another theorem which is joint work with Richard Chua, Sekirich, Lachel, Sherman, which says that a G perf is singular as a stack in codimension 10. And then in codimension 10 you find some cones which are just not simplicial cones, and they'll give you singularities, and no level structure will ever. Well, yeah, I mean, put g greater than or equal to 4. For g equal to 2 and 3, it's smooth. Okay. And now what we can do is here. This tells us a little bit, but I haven't really thought about this. Though it might be, well, it might be worth thinking about. So from this we get the intersection cohomology is isomorphic to ADG g plus 1 minus k perf q this range. Now, a question which I would like to ask is the following. We always have from intersection cohomology to this homology we have a surjective map in the stable range, because everything is algebraic here, so we can lift it to intersection cohomology in the end. And the question is, can this map, or is this map an isomorphism? And I have absolutely no opinion whether I should expect that to be true or not. I just don't want to make any statement whatsoever about it. The very final remark is that there is, well, there's some announcement due to Gian Siracusa and Sankaran, also for stable stable cohomology for the matroidal locus. But okay, possibly with half integral coefficients. I know that what they've been looking at it doing is very similar from what we are doing. They are looking at this very much more in the spirit of the Charney and Lee paper. So take some finite CW complex, study it, look at the cohomology of that. But it might get a little bit more, possibly about integral or half integral coefficient for the cohomology. But I haven't seen the paper, so I can't say anything about this. Okay, this is all I wanted to say. Thank you very much.